All right, now let's use what we've learned. We've worked hard in the last video to show that if you have two different bases for the same span, then they have the same number of elements. All right, so we just showed that the number of elements in a basis doesn't depend on the chosen basis, but only on the span itself. This allows for the following definition. I have a span, the dimension of S, and I'm going to use dim S as a shorthand, is the number of elements in any basis of S. So I don't have a unique basis, so I can't say in the basis. That's why we needed the last theorem. We needed the last theorem to tell us that it didn't matter which basis you picked, they all have the same element. All right, so I want to prove in example 7.4.6, I want to look at the dimension of Rn. If I want to know the dimension of Rn, I need any basis. So we had one that we liked, 1, 0, 0, 0, 1, 0, and so on. We called it the standard basis, but that doesn't matter here. It's just a basis of Rn. And it has 1, 2, up to n. And so that means that the dimension of Rn is n. All right, so the dimension of a span is what's important. That's what tells us about its geometry. Following takeaway 22 on page 168, we get the following correspondence between the dimension of a span and its geometric characteristics. All right, so let's see. Dimension 0. Well, that's just the point. And so the geometry is, well, I guess 1 point. Maybe the origin. All right, dimension 1. All right, so that means you need one generator. So you have your one generator, and you take all multiples of it, and so you get a line. And so this one is a line. And this point that used to be purple that we can barely see now, this is 0. So it's a line containing the origin. So it's the same thing that we had in R3 or even in R2, but now it works in Rn. All right, so dimension 2, that means you have two independent directions. So let's put V and W. They are starting at 0 as well. So these independent direction will give you a plane. And so this will be a plane in Rn containing the origin. All right, and so on. For 3, 3 we can still picture. I have 3 really non-coplanar vectors, something like that. And so I would get some sort of 3D object. Sorry, this is the worst cube I've ever drawn. Let me try again. Up, 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 up. Yep, that's better. So we don't really have a word for this. In R3 it would be just R3, but in general it'd be like a copy of R3 somewhere in Rn. Just like a plane is something that looks like R2, a line is something that looks like R. So this is an R3-like object, but in Rn. All right, I can't even start drawing this one, but this would be an R4-like object in Rn, and so on. So the dimension tells you which of the Rn's it looks like. Is it a line? Is it a plane? Is it a 3-space? All right, let's do one example. So this is example 7.4.7. It's the last one of this section. So consider S, which is the span of three vectors, 2, 3, 1, 1, 4, 3, and minus 1, 6, 7. I'm asked to find the dimension of S. The dimension is the number of elements in any of its bases. So let's find a basis. We have our method. I'm going to put these vectors here, and I'm going to get minus 2, 3, 0. So I have two leading ones. That means I must take the two corresponding vectors, and so B will be 2, 3, 1, 1, 4, 3, and dimension. So dimension of S is the number of elements. Let's write it this way, sharp B, and so that's going to be 2. The whole plane using it. So dimension of S is 2. That means S is a plane through the origin in. To know which Rn you're in, you just have to look at how many entries you have here. We have 3. These vectors are in R3, so the span will be in R3. That's it. Oh, 3 with an H. All right, so it's a plane in the origin. Find an implicit equation for S. So you have two options. You have the geometric solution and you have an algebraic one. If I try the geometric solution, that one will work because we're in R3. What I have is I have my two vectors. So what were they? I have, let's call them V1, V2, and then I have the normal vector. So I'm going to take my normal vector to be V1 cross V2. That means 2, 3, 1 cross with 1, 4, 3, 2, 3, 1, 4, and I get 9 minus 4, 1 minus 6, 8 minus 3. I get 5 minus 5, 5. And so the pi will be 5x minus 5y plus 5z equals d. And then if I plug in my point, we know it's through the origin, so that point we could always take to be 0, 0, 0. I'm going to get that d is 0 plus 0 plus 0, and so here's my solution. This solution requires cross product, which only exists in R3, and so because of this, I won't be able to use the similar solution in Rn. So let's try to come up with an algebraic solution. So we know that we're looking for S, which is the span of V1, V2. When we learned about span, we learned method to find conditions on x, y, and z, and in some sense that's what we want, right? We want condition on x, y, and z, so I'm going to follow that method. So I'm told then that I should put v1 here, so v1 is 2, 3, 1. I should put v2, 1, 4, 3. And then I'm wondering which vectors I can build. So my constant are going to be an arbitrary vector. So in this case, x, y, z. And then I want to reduce. I want to reduce until the coefficient matrix is in REF. And then whatever rows of zeros, the constants must be 0 as well in order to end up with a solution. So I'm going to solve this. Let me solve it the long way without using magic. I like to pick a leading one in the first column. I'm going to pick the 1. And so the first thing I'll do is R1 switched with R3 to bring my leading one to the top. I'm going to get 1, 3, Z, and then 3, 4, Y, 2, 1, X. All right, so once I have my leading one atop, I'm going to use it to clean the 3 and the 2. That's going to require row operations. I'm going to take row 2 minus 3 row 1 into row 2, and row 3 minus 2 row 1 into row 3. All right, let's do this. I get 1, 3, Z. That one hasn't changed. 0, 4 minus 9, that's minus 5, and I get y minus 3z. And then 0, 1 minus 6, that's minus 5. I get x minus 2z, sorry. And then finally, I'm going to use, I have my leading one, this is clean, I'm going to use this leading one. I don't need to clean up the 3, it's going to be messy anyways if I do, so I'm not going to bother. I'm just going to clean up the 5, row 3 minus row 2 into row 3, and I will get 1, 3, z, 0 minus 5, y minus 3z, 0, 0. And then that's the important bit here. Sorry, I'm really low on space. Let me move it a bit this way so I can actually write it in a readable way. So here I'm going to get x minus 2z minus y minus 3z. So I'm going to get x minus y, and then minus 2z plus, so plus z. All right, so what I have right here is a row whose coefficients are 0, and so this needs to be consistent. And so the constant needs to be 0, so I will get x minus y plus z equals 0. That's the equation I will use for this plane. All right, so the two solution gave you slightly different answers, but if you multiply the bottom one by 5, I'm going to get the top one. So they are representing the same geometric objects, and so we're happy about that.